They're pretty qualitative more so than quantitative, but I just want to show you how you can implement Ohm's law to deal with circuit analysis. So let's suppose we've got some circuit here. We got a, should be a familiar circuit. You'll do this in lab. We got a 9-volt battery, one resistor, and an LED. We'll call this R. And just to show this LED, I'll put a little bit of light coming off of it. Anyway, now if you think of your battery kind of like a pump and these wires like a pipe, you can see that there's really only one path for the current to flow, and so we'll just call that I. So the resistor and the LED are connected in series. So now if I wanted to know everything about this circuit, if I want to know the voltage drop across the resistor, the LED, and the current flowing through all this stuff, there's a lot of ways I could solve this. Between Ohm's law and between having a multimeter, there's a bunch of ways I could deal with this. One way would be to look at Kirchhoff's voltage law, which the way that that's stated is that you can't have an accumulation of voltage. If you have a complete circuit, you're generating 9 volts here, and you're using it in these two components, the resistor and the LED. So another way to think of that is if I consider a source negative and these two uses as positive, I could say that we basically have 9 volts plus our voltage drop across our resistor plus our voltage drop across our LED. That all has to equal 0. And there's lots of things, lots of ways I could solve it from here. The LED I'll talk about in a little bit, but say this is, I think in your kit I've either given you a red or a yellow LED. So we're going to assume voltage drop across that is 2.2 volts. And so we can substitute that in. And so maybe we get, and you'll want to follow the directions in the lab. It may not be 2.2 volts. I think I have you measure it though. So maybe we measure that quantity. So if that VR plus 2.2 volts. So if we simplify this, we can get that the voltage drop across our resistor there is just going to be 6.8 volts. Now, that tells us our voltage. If we want to know the current, though, we can look at this resistor and say, you know, another thing VR equals, VR also equals I times R. So depending on what I know here, maybe I know the resistance value, in which case I can solve for I. So it all just depends what pieces we need. I should also mention to measure any of these quantities. Suppose I want to measure the voltage drop. I'll make blue my voltmeter. How's that? In order to measure, say, the voltage drop here and get our 2.2 volts across our LED, we would connect the voltmeter in parallel. And that way we're measuring the voltage drop across these two terminals. And I should point out the resistance inside this voltmeter should be pretty close. It should be a really big number because we don't want any current or as little current as possible going through this loop. Because if current's bleeding through this loop, we're lowering the voltage across this LED, and so we're taking a measurement and we're affecting it by measuring it. So that's always a bad thing. So when we measure voltage, we connect it in parallel. So if I wanted to measure voltage here, I'd literally take my voltmeter probes and put it there. So I can measure it that way. Now, if I wanted to measure current, that's a little different. Current has to be measured in series. So I actually have to break the circuit somewhere in that loop meaning take the wires out, and then I have to put the ammeter in series like that. That way I measure the current going through the circuit there. And in that case, we want resistance to be as close to 0 as we can get it, because we don't want any voltage drop across this ammeter. We want the current to just flow straight through. And another way to think of this is if I was measuring pressure, switch back here, if I was measuring pressure in this pipe, pressure drop across a valve or something like that, I would measure it in parallel, right? You know, maybe I've got this in parallel. If I wanted to measure the flow through, and I wouldn't want a whole lot of my water bleeding off and going through this, through my my pressure gauge. I would want it to just measure the pressure difference there. Same goes for ammeter, for the ammeter. If I wanted to measure water flow through a pipe, I would want it to be in series so that all the water going through here goes directly through my flow meter. And I would want this to provide as little resistance as possible. I'd want it to look just like this straight section of pipe so that I can measure and know that, you know, I'm not restricting the flow at all. So that's just what I wanted to say about that. So I'm going to go ahead and clear this frame. That was a series circuit. And we'll move on to a parallel circuit once my computer responds here. There we are. Okay. So for a parallel circuit, what makes, say, resistors in parallel, you know, maybe in physics class you had this nice little R1, R2, and maybe these are perfectly parallel lines. That's the way they're drawn in your book or whatever. But what's far more important than whether or not they're actually parallel lines is, see how there's no components up here? These are basically, this is just a regular piece of wire with very little resistance. So we call this a node. And same with this guy down here. This is another node. So what makes these parallel is that they share the same two nodes. And what that means is all of these have the same voltage drop across them. Whether it's R1, R2, doesn't really matter. Because they share these two nodes and they're in parallel, they all have the same voltage across them. Why that's important is sometimes you'll see some sketch on a napkin, which is not much different than what I'm sketching anyway. I mean, this is not great art. But, oh yeah, we got all these resistors that kind of look like this. And believe it or not, those are all still in parallel. Even though it's like, well, what is this mess? Well, if we look at our nodes, we can say, you know, here's one node, and here's the other. So, this was 9 volts. This one has 9 volts. This one has 9 volts across it. This one has 9 volts across it. 9 volts. Hey, I didn't do too bad drawing these upside down. Anyway, they all have 9 volts across them. And this would be a really poor way to draw this, but it still works. These are all in parallel. So, why this is important is we really want to keep track of these nodes. If we have current flowing out of here, gets to this point, and it has two options. So maybe we call this I source. Then it gets to this point, some of the current goes this way, we'll call that I2. Some of it goes this way, and we'll call that I1. We know that we can't accumulate current here. So, KCL, or called current law, says that if we have current flowing into a node, it also has to leave the node. So, I could say our source current plus I1 plus I2 equals 0. Any current that comes in has to leave. And so using your mathematical abilities, you can figure out all sorts of things with this, depending on what you've measured, what you know, and what you can find out from KCL and Ohm's law. So one last thing I wanted to show. I kind of avoided the LED, and I'll explain why. Oh, I don't want background, I want a clear. Okay, so I'll graph out some stuff for you here. If you truly believe Ohm's law, which I hope you do at this point, and it's science, so you don't have to believe it, you can just, prove it if you want. If I say this is current, I should release this line here. Suppose I have current and I have voltage. And we think about Ohm's law. We'll manipulate it. We'll make Ohm's law. We'll solve it for current. Okay. So in the case of a resistor, we have something like this. Because we could think of this. This is for a resistor. This is like E, that's like 1 over R times E plus 0. Y equals mx plus b, right? It's a line, it's linear. If we change the voltage just a little bit, the current will change depending on our resistance. And that's great. We like that. Cross is right here at 0. Our intercept is 0. Hey, this is all great. That's all good in the world. We like resistors for that reason. However, there are some nonlinear components like an LED. And they look more like this. I should put there's an X out here somewhere where the resistor catches on fire, but whatever. LEDs, it's a little bit more of a concern. And the reason is, first off, we stay pretty close to 0 for a really long time until we reach some knee voltage or a turn-on voltage. And maybe this is 2.2 volts for a red LED for just a standard silicon diode, something like that. Whatever it is, you're going to have some knee voltage where below that you don't have hardly any conduction. But then after that, a tiny change in voltage can result in a big change in current. And so that's going to be important. It's not linear. Now, this isn't to say Ohm's law doesn't exist. It very much does. Any point along here, our instantaneous resistance follows Ohm's law. But the thing is, we have to look at it in terms of instantaneous resistance, not in terms of just some big general slope like you can for a resistor. So, this is going to be important. We're going to worry about that a little bit throughout this class, because it may be that this may be 25 milliamps is where this blows up. So we may be designing circuits that have a resistor in there to lower the current in the overall circuit so that we don't burn up our LED. Okay, so that's mostly what I wanted to say about both of those. So